My name is Gábor Kovács. I came from the Rényi Alfréd Institute of Mathematics, and I have created the opening slide in archival format. I hope you can read it. If not, there is a clean version of it. So I would like to speak about the artificial intelligence in archives, and highlighted the optical character recognition processing methods which we applied. So just to introduce the projects, we are working with 3 different Hungarian archives: the historical archives of the Hungarian State Security, the National Archives of Hungary, and the Budapest City Archives. Our long-term goal, or the main goal, is introducing different kinds of artificial intelligence-based applications into the pipeline, into their processes. I would like to briefly introduce these kind of topics at the end of my presentation. And I would like to introduce detailed our short-term goal, which is establishing the feasibility of the applications, and the long-term goal by creating foundational models. So our main challenge in these projects are the quality of the data. At the archives, we have millions or hundreds of millions of document pages, unfortunately in a very degraded and very bad quality, which are pretty challenging to get processed. So maybe if I zoom in the picture, you can see that the letters are missing, and sometimes they are pretty transparent, so it has a pretty poor quality. What problems do we have to solve because of the data? So we would like to implement different kinds of applications which requires the extracted text from these kind of document images. So we would need an optical character recognition system. But unfortunately, the off-the-shelf already existing OCR systems are mostly form-born digital documents and underperform on this kind of degraded historical data. So we can train different kinds of AI models, but in order to train them, we need supervised or labeled data, which we don't have. And there are 2 approaches for creating this kind of supervised data. The first one is applying human annotators, but this is a very slow and expensive procedure. And we opted for the second approach, which is we want to create our synthetically generalized data. So I would like to introduce this kind of framework. Here you can see the 4 stages of the generation of a synthetic document image. What makes our framework pretty useful is its modularity. We have different points where we can adjust the details of the generation. For example, we can use different kinds of languages, we can apply different kinds of font types and different kinds of layouts, for example, tables, paragraphs, and so on. We can add domain-specific background images. In this case, we selected a couple of degraded historical paper types and those papers that can be found in the archives. And we implemented more than 20 different kinds of domain-specific noise perturbation, for example, which makes the text transparent, or adding different kinds of additive texture noise, or putting overbleeding text from the other page of the document. And we apply a couple of geometric transformation, for example, waving or rotation of the image. So what are the tasks we can train by using this kind of data? The first and most important task is the so-called document image enhancement. It's about getting a noisy image and transforming it into a cleaned image. The second task is text detection, so where we have to detect the bounding boxes or the areas where there are words or text lines. Another task we can use our data generation pipeline is text recognition, so it's the OCR, or the optical character recognition task. This is the step when we extract the text itself from the image. Another task is the layout detection, where we have to identify different kinds of layout parts in the image, for example, paragraphs, titles, images, tables, and so on. And the final task we can solve by using this framework is the task of reading order detection, where we have to define the order of the already extracted layout parts. So we have trained a couple of foundation models using this kind of synthetic data generation pipeline. The first model I would like to introduce is our document image enhancement model. This model, for those who are interested in the AI details, is built on a UNet architecture, which is pretty effective in image-to-image transformation. It's a kind of de facto standard for denoising tasks. It builds on convolutional operations, which are great at extracting image representations, has an encoder and decoder structure, which are great at localizing local and global patterns or objects, and builds on skips connections, which gives a very handy reparameterization of the problem. So the advantages of using this kind of DIE model is that after we cleaned the noisy document images, we can apply off-the-shelf OCR systems, for example the Tesseract or ABI, which otherwise underperforms the task. And we have a clean version of the document image. Let me show you a couple of demo examples. So on the left you can see the original degraded noisy image from the Magyar Nemzeti Levéltár or database. And on the right side you can see the output of our DIE or document image enhancement model. There's another example. So fortunately it can remove a lot of noise. And yeah, the image on the right side can be processed by existing OCR systems. But to take advantage of the recent advantages or advances of AI models, we want to train an optical character recognition model as well. We opted for the so-called TR-OCR model architecture, which is kind of a state-of-the-art in the literature. It's based on a transformer architecture, which is a highly capable model. It harnesses the attention mechanism, and it's very scalable. It also has an encoder-decoder structure. Encoder part is responsible for the vision or the image preprocessing parts, and the decoder is for the language modeling parts. And yeah, it can take language knowledge and insert it into the OCR pipeline. So the advantages of this kind of approach is we can ingest the different kinds of image processing steps into the transformer architecture. And this kind of modular architecture is great for example, if we want to go to another language, we can change the decoder part of the model, and we can support different kinds of languages, or we can apply multilingual models as well. So the applications we would like to create in the short future. The first one is about named entity recognition and graph-based data structures. So on the first step, we have a raw degraded image, which we clear using our DIE model. After that, we can extract the text written on the document page, and using some kind of named entity recognition classification model or a large language model fine-tuned to this task, we can classify different kinds of named entities, for example, persons, locations, or dates. And after we have these kind of entities, we can build a representation of the data, for example, a graph, which is pretty useful in other applications and in queries when we have to explore the dataset at the archives. Another application is about removing sensitive information from the document images. So again, we have a raw scanned or we have a photo of a document. We apply optical character recognition to extract the text. After that, we have a pre-trained or fine-tuned large language model, which can process the text semantically and can identify abstract concepts. So we can outperform basic keyword search, and we can find highly abstract notions and parts in the text to remove different kinds of sensitive information. After some image manipulation, we have the original image of the document, and the sensitive parts have been removed or covered from the paper. And for example, if somebody requests some documents in the állambiztonsági szolgálat történeti levéltára, then you can get the documents, but some of the personal and sensitive data must be removed, and this kind of application is pretty good for that purpose, because it's currently being performed by human workers, and it's quite a bottleneck in the process. So our last application would be a so-called digital historian. So as I have already mentioned, there are a lot of millions of document pages at the archives, and there are researchers who perform different kinds of researches on this kind of data. We could transform this data, after we have extracted the text using OCR models, into a vector database, and we can leverage a large language model in a retrieval augmented generation setup. So from now on, if a researcher can define a query, for example, what was the most significant event in Hungary in 1925, then our system could give an answer that the establishment of the Hungarian radio, and not just provide the answer itself, but also give some clues, the hit, so the documents itself, where the information come from. So this was the last application I wanted to talk about. Thank you for your attention.